This is your page 175 assignment, and I'm going to give you some helpful hints on numbers 8, 22, 26, 35, 37, and 38. So let's start by taking a look at number 8. The directions say to complete this two-column proof below. Let's look at our given. We are given that line AB, that's this one, is perpendicular to line BC. And we're also given that the measure of angle 1 plus the measure of angle 2 is 180 degrees. Given that information, we're going to prove that line BC is also perpendicular to line CD. All right, so looking at the proof, first of all, we're given that AB is perpendicular to BC, and also that the measure of angle 1 plus the measure of angle 2 equals 180. Where did this information come from? Well, it came from your given statement. And by the way, you don't need to write this entire proof on your homework paper. You just need to write the blanks that you're filling in. All right, so if 1 and 2, if their measures add up to 180, step 3 tells us that 1 and 2 are therefore supplementary, and we back that up with the definition of supplementary angles. Okay. And now, step 4, okay, we have these two angles supplementary, okay, so what must this statement be if we're backing it up with the converse of the same side interior angles theorem? Now, I want to remind you what that theorem says. I don't want you to write the name of these theorems on your proofs. I want you to write the shorthand of the theorem. So the converse of the same side interior angles theorem says if we have same side interior angles supplementary, we may conclude that we have parallel lines. Okay, so we've just shown that we have these same side interior angles supplementary. So what are the two lines that we are concluding must be parallel? Well, that would be line AB and line CD. So your statement in step 4 should be that line AB, remember we name a line by 2 points on the line and the line symbol above it, is parallel to line CD. And the reason why is because when same side interior angles are supplementary, we can conclude we have parallel lines. Okay, so now we have proven line AB parallel to line CD. Okay, we were given that line AB is perpendicular to the first of those two parallel lines. So take a look at either your notes or your yellow sheet and see if you can come up with this theorem. Okay, for step 5, the reason, and it has to do with assuming you have two lines parallel and one line perpendicular to one of two parallel lines. How can we conclude that that same line, that same transversal, is perpendicular to the other parallel line? So look at your notes or look at your yellow sheet and see if you can find this theorem for reason number 5. All right, now let's take a look at number 22. It's a critical thinking problem, and it asks you this question. Are the reflexive, symmetric, and transitive properties true for perpendicular lines? Explain why or why not. All right, so we have a reflexive, symmetric, and transitive property for equality. Remember, the equality is a relationship between two numbers. We also have a reflexive, symmetric, and transitive property of congruence, which is a relationship between two things, like two segments or two angles. Okay, so if you think of perpendicularity, if you will, if you can think of that as a relationship, okay, between two or more lines, let's see if there would be a reflexive property of perpendicularity. Okay, if there were, it would say that a line is perpendicular to itself. So I want you to think about that. Is that possible? If so, say yes. If not, say no, and explain why you think that. Okay. And then the same thing with the symmetric property. If I have a line L perpendicular to line M, then can I turn around and say that line M is perpendicular to line L? Decide yes or no. You might want to draw a diagram in your explanation of why or why not. And then finally, is there a transitive property of perpendicularity? Okay, now a transitive property would always involve 3 or more things. In this case, we have 3 lines. If line L is perpendicular to line M and line M is perpendicular to line N, in other words, I have a first line perpendicular to a second and that second perpendicular to the third, then would it be true that the first line L is perpendicular to the last line N? Okay, again, drawing a diagram might help you decide yes or no and be able to explain why or why not you think it's true. Okay, now let's take a look at number 26. It's a critical thinking question. It says, draw a figure to show that theorem 3-4-3 is not true if the lines are not in the same plane. Okay, first of all, what does this 3-4-3 mean? Well, if you turn back just a few pages in your book, turn back to page 173, you will see that theorem, this is just the way the book names these theorems. It's a theorem that's in chapter 3, it's in section 4 of chapter 3, and it's the third theorem. So that is just your book's way of numbering the theorems. So take a look in your book, and you'll see that it's a theorem that you'll also find in your notes and on your yellow sheet, which says if two coplanar lines are perpendicular to the same line, then those two lines are parallel. Okay, so two coplanar lines, let's just, in fact, I'll just write it in shorthand real quick. If I have two coplanar lines that are perpendicular, let's see, two coplanar lines perpendicular to the same line, then those lines would be parallel to each other. Then those two lines would be parallel. Two lines parallel. Pardon my sloppy handwriting on this air slate. Okay, so what this question is asking you to do is take out the word coplanar. If we took that out, then would this theorem still be true? If two lines that aren't restricted to the same plane are perpendicular to the same line, then would those two lines have to be parallel? Okay, so think of a picture you could draw. I saw a student today had a picture. It kind of looked a little bit like a wedge of cheese. Let me see if I can redraw that. Okay, if you can imagine a triangular prism or a wedge of cheese. Okay. Something like that. Okay, not a very good drawing. But anyway, if I'm going to draw a segment on this side of the wedge, okay, that's perpendicular to this edge, and then draw one on this side of the wedge. This is not a very good drawing. I'm sorry, guys. Okay, then we would have two segments perpendicular to the same segment, but they are not parallel to each other because they're not in the same plane. Okay, again, think of a wedge of cheese or a triangular prism. All right, so see if you can come up with another example. The example I have used is if you've ever seen those signs, where those direction signs where there's a post, and then there'll be one sign here that says go this way to go to New York or something like that. Okay, this sign would be perpendicular to the post, and then another sign pointing in a different direction, go this way to go to California, let's say. All right, and then that sign, notice that, again, not a very good drawing, but two signs that are perpendicular to the post. However, these two signs are not parallel to each other because they're not in the same plane. So see if you can come up with another idea or another drawing that would show that this theorem is not true if the lines are not in the same plane. Okay, taking a look at number 35, just wanted to give you a couple of hints on this one. First of all, you have a description here. Make sure you draw a diagram of what's going on. Lines M and N are parallel. Line P intersects line M at point A, and line N at point B, and is perpendicular to line M. So in order to answer these questions, you're really going to need a good diagram. So draw a diagram of exactly what is described here. Okay. Once again, I think you'll be okay with letter A. When you get to letter B, when it says, what is the distance from point A to line N? Okay, your answer will not be a number. You're going to express your answer as the measure of a segment. Remember, when you write the measure of a segment, you'll write the names of the two endpoints with no bar over the top. So think about answering this question. And also this question, what is the distance from point B to line M? Again, you will write your answer in terms of the measure of a segment, and you'll also answer part C as well. How would you define the distance between two parallel lines in a plane? Okay, well, it will have something to do with the measure of the shortest distance between those 2 points. So you might want to look at that definition on your yellow sheet, the definition of the distance from a point to a line. Okay, moving on to number 37. We're going to prove one of the theorems that we talked about in our notes. I'm going to get you partway through this proof and then expect you to finish it on your own. Okay, so again, this is how your book numbers these proofs. It's if you look back a couple of pages, you'll find the theorem 3-4-1, chapter 3, section 4, first theorem. Okay, it says if two intersecting lines form a linear pair of congruent angles, then the two lines are perpendicular. Okay, now I numbered off my statements and my reasons and forgot to leave space for the given and the proof statement, so we're just going to write them up here. Okay, remember the given statement is the information that comes from the hypothesis. I'm going to underline that once. And we're going to write it in terms of the diagram. Okay, so what are we assuming? Two intersecting lines form a linear pair of congruent angles. Okay, so let's go over here to our diagram. Let's label these angles 1 and 2. Okay, so what are we assuming? That we have a linear pair. So we're going to assume that angle 1 and angle 2 form a linear pair. Okay, and it also says in the hypothesis a linear pair of congruent angles. So let's also assume that angle 1 is congruent to angle 2. Now, given that information, we're going to prove the information in the conclusion. So let me underline that twice. The two lines are perpendicular. So that conclusion in terms of this diagram, our lines are L and M, so we're going to prove that L is perpendicular to M. Okay, so now, I don't think we've been writing proofs long enough now. I think it's not going to throw anybody. I'm going to put both of our pieces of information in one statement, both of our pieces of given information in one statement. So we are going to assume that angle 1 and angle 2 form a linear pair, and to save space I'm going to abbreviate that. Okay, and we're also going to assume that angle 1 is congruent to angle 2. All right, why is that true? Because we said so. That's why we're just going to assume that those two pieces of information are true. Okay, now if angles 1 and 2 form a linear pair, okay, then we have proved that angle 1 and angle 2 are supplementary. All right, look at your blue sheet and find a theorem that we have proved that backs that up. I'm going to leave that for you to do. Back up that if I know that angle 1 and 2 form a linear pair, how do I know that they're supplementary? Okay, if I know that they are supplementary, then in step 3, I'm going to say that the measure of angle 1 plus the measure of angle 2 is 180 degrees. Again, I'm going to leave it up to you to come up with that reason. Okay, what backs up? If I said that angles 1 and 2 are supplementary, why can I say their measures add up to 180? You go back and find that reason. Okay, now going back to our given, remember we also assumed that angle 1 was congruent to angle 2. So if I assume that those two angles are congruent, I can say that the measure of angle 1 equals the measure of angle 2. And again, you come up with the reason. Okay, we assumed, we were given that angle 1 and angle 2 were congruent, so what guarantees that their measures are equal? Okay, now I'm going to do one more step with you. What I'm going to do is I'm going to take step 3 and I'm going to rewrite it, except I'm going to replace the measure of angle 2 with what it is equal to. So instead of writing the measure of angle 1 plus the measure of angle 2 equals 180, since in step 4 I said the measure of angle 2 is the same thing as the measure of angle 1, I'm going to say the measure of angle 1 plus the measure of angle 1 again is equal to 180. Now, what is that reason? I'll give you a big hint. I just replaced or substituted the measure of angle 2 with what it's equal to. Okay, then I'm going to give you one more step, and I think you'll be able to take it from here. I'm going to add these two together. The measure of angle 1 plus the measure of angle 1 would be the same thing, would be equal to 2 times the measure of angle 1. So again, I just made a replacement or a substitution. I replaced the measure of angle 1 with the plus the measure of angle 1 with what it's equal to. Okay. Then I'll just give you a few hints for the last steps. If I were to divide both sides by 2, I would have the measure of angle 1 is 90. Okay. Now look at your diagram. If the measure of angle 1 is 90, then it's what kind of an angle? Tell me what kind of an angle it is in step 8 and back that up. And then in step 9, okay, if I know that angle 1 is a right angle, then I'm going to be able to say, let's go back to our proof statement. I'm going to be able to say that L is perpendicular to M, and again, I want you to come up with that reason. All right, and last but not least, let me give you a little bit of help with number 38. We're proving theorem theorem 3-4-3, which says if two coplanar lines are perpendicular to the same line, then those two lines are parallel to each other. So let's write a given and a proof statement in terms of this diagram. So what would we be given? What would we be assuming to be true? Okay, two coplanar lines perpendicular to the same line. So we look at your diagram. In terms of this diagram, we're going to assume that line R is perpendicular to line T and line S is perpendicular to line T. Given that, we are going to prove, what's the conclusion? That those two lines are parallel to each other. The two lines being these two lines, okay, parallel to each other. We're going to prove that R is parallel to S. Okay, so this proof is actually going to be pretty easy. It's only going to take you 4 steps if you combine your given statement, both of these pieces of information in one statement. So if you're given that R is perpendicular to T and S is perpendicular to T, look at your definition of perpendicular lines and you can conclude that you have some right angles here from the definition of perpendicular angles. All right. Now, if you have two angles, let's call this one angle 1 and this one angle 2. Okay, you can say that they are right angles from the definition of perpendicular lines. Then they are congruent to each other because of a little theorem we proved. You'll find it on your blue sheet that says if two angles are right angles, then they are congruent to each other. And then look at the positions of 1 and 2. Okay, aren't 1 and 2 corresponding angles? So since you've proven that they are congruent to each other, then you're going to be able to say that line R is parallel to line S, because when two lines are cut by a transversal and corresponding angles are congruent, then those lines must be parallel.